left last time. So let me, we've done a lot of things, so let me try to summarize what we're up against, right? And then we'll provide in more detail, but let me give you some pictures or some drawings before we actually get into math. So here's what we are dealing with. You know, we started by talking about Fourier transform, and this is what we said. There is a direct Fourier transform x of omega is equal to integral when t goes from minus infinity to plus infinity x of t e to the minus j omega t dt. So this integral here allows us to go from the time domain into frequency domain, and it tells us what is the frequency content of the spectrum, or of the signal. What are the sinusoidals or range of sinusoidals that participating in building that signal. This is what we call continuous Fourier transform, or continuous CFT, continuous Fourier transform. Our way back from frequency domain into time domain is this integral, 1 over 2 pi integral when omega goes from minus infinity to plus infinity x of omega into the j omega t dt. So this is our inverse continuous Fourier transform. Now both of these are continuous transforms, right? What it means, they're very nice, you know, when you do whiteboard work and when you do homeworks and stuff like that. But you know very well that when we try to compute something, like for real, when you try to do it for something that is real world related, that we rarely can do anything in continuous domain. Our machines for computing are discrete, digital, right? So what we would like to do in any practical circumstance is evaluate this integral by using numbers, by using discrete values. And we already started doing some of that. We said, well, you know, so what that means using discrete values is that I want to be able to compute the Fourier transform, but not based on the signal itself, but instead based on the samples of the signal, you know, quantized samples of the signal. And as a result of that, you know, you will see I'm going to get also some numbers. Well, what these numbers are going to represent are not the actual x of omega, but the samples of the frequency content of the signal. So we're going to be going from samples in the time domain to samples in the frequency domain back and forth. So what I need to do is somehow translate these two equations, which are continuous domain equations, into something that gives me operation on a discrete set of numbers in one domain versus discrete set of numbers in the other domain. Now we already have tools for that. We know sampling theorem that tells me what is the proper way of sampling theorem in time domain. It tells me what is the proper way to sample the signal in time domain so that I preserve all the information. And we saw the implications of sampling as well. Now last time also we went over sampling theorem in the frequency domain, which tells us how to sample the frequency of, how to sample the signal in frequency domain so that you can reconstruct it again. And we saw that two of them are dual of each other. So what I need to do today is connect the two. Connect the sampling in the time domain, connect the sampling in frequency domain, and derive the counterpart of these two equations that are all based on samples. Samples in the time domain that will relate to samples of the frequency domain and vice versa. Now, when I do that, it is important for you guys to be very careful because you will realize that I cannot do this exactly. You know, there will be some approximations that are a result of that. And you have to understand what those are and what are the limitations of this method, because this is the most frequent way of why, I guess this is very common that you would misinterpret what you're actually seeing by not understanding the relationships between all of these sampling and time. So before I go and as I said, and do some math, let me actually draw some pictures that illustrate the process that we're going to be following. So here is where we start. We start with our signal in the time domain. Let's say this is our signal x of t. And let's say x of t. And let's say this is our boundary between time and frequency. And what you're going to have in the frequency domain as a result of this Fourier transform, this is going to be x of omega, right? The Fourier transform associated with this x of t. We know one basic truth to hold, and this is that if this x of t is an energy signal, essentially non-periodic energy signal, then this x of omega is made, this x of omega exists, right? It's Fourier transform. But there's another truth that we know, and you have to be cognizant of this one. Let's say this signal, I cut it, right? So it's finite in time. If the signal is finite in time, what will happen to its Fourier transform? It's going to become infinite. Remember, if I take any signal x of t and I cut it in time, this is equivalent to multiplying this signal with a pulse, right? Now, when I multiply with the pulse, what is the Fourier transform of the pulse? Sinc. Sinc is an infinite in frequency domain. Multiplication in the time domain is convolution in the frequency domain. So if I process the signal as a whole, then I have a chance of this x of omega being finite in the frequency domain. But if I just take a piece of this signal and I process it as I always do, right? I can never wait for infinity for any signal. I'm always going to take a chunk of it in the time domain. Then my x of omega is always going to be infinite, right? So be cognizant of that fact. So that's the starting point. So then the next point is I'm going to do two things. I'm going to take what I just said. I'm going to take a chunk of this signal in the time domain. Let's call this tau. And I'm going to sample it, right? So this is how it's going to look like. Now, what is the frequency? And then samples here, I'm going to assume are equal to 0. Okay? So as a result of, this is my x truncated of nTs. Ts is this this sampling interval here, which I know has to be larger than smaller than 1 over 2 times the bandwidth of the signal, right? So what are the consequences of sampling in the time domain? Is periodic extension in the frequency domain. So the result of this sampling is I have this. I have my original signal here. This is my Fs. There's a periodic extension. And there is a periodic extension all across the frequency x. So my x of sampled, x bar of omega is going to be equal 1 over Ts sum x of omega minus n omega s. Omega s being the angular sampling frequency. Now, this formula that I have here is taking this signal and periodically extending it. But there is a caveat here. This formula here assumes that I'm sampling the original signal. So my sampling sequence is infinite. That's never the case. So as a result of that, when you do this in practical work, practical scenarios where you truncate the signal in a time domain, you cannot avoid aliasing. Why? Because the fact that I'm truncating the signal in a time domain will make its spectrum infinite. So even though I'm, and my process of sampling will do replication of this spectrum, but because the spectrum is now infinite, there will always be an overlap here. Okay? Now that overlap, what is the way of dealing with it? The most common way how we deal with this, well, we say let's not sample at exactly Nyquist rate. Let's sample a little bit higher, because that will separate these more. So hopefully the aliasing here is going to be insignificant. And rarely, if ever, you actually sample at the Nyquist rate. You always sample at something that's high. And the reason for that is, I mean, there are multiple reasons. One is to help the reconstruction. But one of the most important reasons why is because you're always operating on a finite portion of the signal. And as a result of that, you're actually looking at distortion in the frequency domain where the spectrum is broadened by the fact that you're looking the signal in product with a square pulse. Therefore, by using the sampling frequency, which is higher than Nyquist rate, you're pushing these replicas of the signal further apart, allowing you to have less of a distortion when it comes to aliasing. Now, the last step of the puzzle is doing this. I'm going to take my original signal, and I realize I did very poor choice of the shape here, but let me do it. I'm kind of stuck with it now, so let me do this. Now, what I'm going to do is I'm going to take my signal, now sampled one, and perform the periodic extension of this signal in a time domain. Right? So I'm actually just observing this tau duration of the signal in a time domain. The signal behaves differently in reality past this point, right? In this case, it might go like this, right? Whatever it looks like. But I'm ignoring these, and I'm taking this signal here, and I'm replicating it in the time domain. As a result of the replication in the time domain, what happens in the frequency domain? In the time domain, by replicating the signal, I end up with what kind of signal? Periodic, right? If something is periodic in a frequency domain, what does the spectrum of that signal look like? It is discrete, right? Remember, Fourier series. Fourier series has a discrete spectrum, right? So, as a result of this periodic extension in the time domain, what happens in the frequency domain is this. I no longer have this entire signal, but instead I have all of these samples of this signal. Right? And this is where I'm going. Right? This is what I'm going to actually derive. I want to derive the relationship essentially between this and this. I want to relate these two. The samples of the signals in a signal sample in a time domain take over the finite interval tau with the samples of the Fourier spectrum of the signal that are now separated by 1 over tau in the frequency domain. So, and that's going to be my discrete Fourier transform. All right, so how do I reconstruct my signal? So reconstruction of the signal. I have two methods. Okay, so first one is of the signal from spectral samples, right? Let's say I have these samples of the signal in a frequency domain. How do I get back to my signal x of t? The first method, it says, well, use frequency domain domain reconstruction to recover x of omega. Essentially, going this way, let me see if I don't have a different, but saying use frequency, reconstruction in frequency domain to take these samples and generate this x hat of omega. How do I do that? Well, you saw the last time, the reconstruction formula in the frequency domain is essentially the same as the reconstruction formula in a time domain. I need to take these samples and weight them with the sinc function, and then they would magically reconstruct this back, right? And then after I reconstruct this signal back, then I use filtering in this domain to get rid of all the higher frequency components. So the second step would be use filtering in frequency domain to eliminate periodic extension of the spectrum. And then in the last step, so this would essentially mean go from this into this, right? Get from this x hat, get this back. And then take the inverse Fourier transform of this to get x of t. So apply inverse Fourier transform of x of omega to determine x of t. So this is kind of going from these samples, this route, and then this route. So that's a method one. Okay? So if I take this signal here and I process it by using following, I take the, let's say, Fourier transform, however I get here, either I take the Fourier transform or I sample it, and then I take the Fourier transform of the sample signal, and then I sample in a frequency domain. To get back, I can do, one way to do that is to reconstruct my sampled spectrum, filter the baseband to get the spectrum of the signal, and then inverse Fourier transform leads me here. Method 2 says that I can do the same reconstruction, but using this. I can use sample frequency domain to generate this guy here. So I can go directly this route. So use frequency domain samples to generate discrete and periodically extended signal in time domain. And then just pick one of the periods. That's kind of giving you this path. And then use the time domain reconstruction formula to get here. To estimate x of t. Other methods are possible too. I mean, so far I gave you these two. This is method 1, how you get from here to here. You can take this signal, interpolate in a frequency domain, filter in frequency domain, and then travel through inverse Fourier transform here. But you can here do inverse Fourier transform to lead you, get you here, and then pick one of the period, which is essentially filtering in time domain, and then interpolating here. You can do this. You can go from here, you estimate your spectrum of the sample signal, then do the Fourier transform, and then reconstruction in the time domain. So there are multiple ways how you can reach this, but practically, if you have a sample version of the spectrum, you can do one of these two methods. This one, we have no problems doing, because we know how to travel all the way through here, right? This is what we covered last time. We can take the samples of the signal in the frequency domain, use frequency domain reconstruction formula. This is multiplication in a frequency domain, which is essentially convolution with the sink to get us this, right? So we have no problem. What we need to understand is, how do I go from here to here? This is what we need to cover. This relationship here is what we need to present today. The rest of it, we actually know all of it how to do. We kind of know how to do this in principle, and that's what we're going to use to actually derive the formulas. You know, we need to actually do the extension, apply a Fourier transform, and then see what happens. And what you will see happening is two sets of formulas that will look almost like these two, but that will be very, very, computer friendly. They will be really nice for computation in computers. So let's travel there. But before we go there, let me address some relationship here between these timings and number of samples and so on. So let me just talk about a little bit about timing here. So here are the observations. First observation, that number of samples in tau, or let me call this a little bit to be consistent with the rest of it. So I'm going to call this T0. I apologize for that. Let's call it T0, because I think in the rest of the notes this is called T0. What is T0? T0 is the is the portion of this x of t that we cut and then perform the periodic extension. So the number of samples in T0, I'm going to call that n t, and this is obviously T0 over Ts. Ts is our sampling interval. So basically what I'm saying here is, in this period that I've selected to process my signal, this chunk of the signal in the time domain, I'm going to have nt total number of samples. Right? This is the number, it's kind of funny to say, the number of numbers, right? Or the count of the numbers that I have at my disposal to try to estimate what my frequency domain representation of the signal look like. The second observation is number of samples, in T0, which is period in time domain. Number of samples in frequency domain period. Let's see, one period in frequency domain. Let's call that NF. Well, let me ask you this. What is the period in a frequency domain? How long before this spectrum starts repeating? What is it that we say? It's periodic extension here. What's the period along the f-axis? What is it? This is the spectrum here, then repeats again after fs 2fs, 3fs, and so on. So the sampling with the time domain rate of fs actually extends the periodically signal in the frequency domain. Every fs you have the replica, right? So the period is equal to fs. But what is the separation between these two? Well, we saw the last time that based on a frequency domain sampling, the separation between these samples in a frequency domain is equal to 1 over t0, where t0 is the length of the time domain that you're using for processing. So this is fs over 1 over t0, which is essentially fs over f0, however you want to look at it. So an interesting thing is to observe is this. This fs can be written as 1 over ts, and this f0 can be written as 1 over t0. So this becomes t0 over ts. So therefore, nt is equal to nf, right? So that's very important observation for us, and then it gives us, we're going to call this n0. So what is it, the message here, the moral of the story? If you take the signal x of t, this is a continuous signal. Let's say I cut t0 piece of that signal, and then I sample this signal at its Nyquist rate, or whatever is the rate that I sample, but higher than Nyquist rate. I'm going to accumulate nt number of samples, where that nt is going to be the ratio of this total time to the sampling time, right? There's going to be nt numbers that I'm going to get when I sample this signal. When I do all of this and eventually get the samples of the Fourier Transform of this signal, what I'm going to end up with is the same number of samples in the frequency domain. So that's the first very important. So what this transformation that we're after here is going to do is it is going to take nt numbers that I have collected in the time domain and translate that into nf numbers that will represent the samples of the spectrum, and these two numbers are going to be the same. So whatever many samples I have in the time domain, that's however many samples I'm going to have in a frequency domain. All right, so I think we have this stage set. So let's go actually and derive the relationship between this periodic extension of the sample signal and this sampled version of the periodic extension of the Fourier transform of the signal. So discrete Fourier transform. So let x of nts be the nth sample of x of t in time domain. And let x of r omega 0 be the nth sample of x of omega in frequency domain. So define xn as ts times x of n ts, which is essentially t0 over n0, right? Because ts is equal to total time that I have for processing divided by the total number of samples that I take, right? And this is this n0. Essentially the count of how many of these samples I'm able to take over the period of t0. x of nts. And also I'm going to define xr as x of r omega 0, where this omega 0 is equal to 2 pi f0, which is 2 pi over t0. t0 is the time that I have available for processing. So Dft theorem says this. First, xr is equal to sum when n goes from 0 to n0 minus 1, xn e to the minus j r omega 0 n. And then second is xn is equal sum when r goes from 0 to n0 minus 1, xr e to the j r omega 0 n. Where this omega 0 is omega 0 t, which is 2 pi, yes, 2 pi over n0. All right, so let's stop for a moment and see what we're claiming here. Except for this scaling factor here, which is not that important, but it's there for just math purposes to make sure everything works correctly. These xn's are the samples of the signal in a time domain, right? I have t0 of duration of that signal, and for processing, and over that duration of t0, I'm accumulating n0 of these samples. Let's say for the sake of explanation, I have hundreds of samples in a time domain of a signal. What this theorem says, I can get 100 estimates of the spectrum of this signal in a frequency domain by performing this operation here, right? So this will give me 100 estimates of the signal spectrum in a frequency domain. And if I had those 100 estimates in a frequency domain, then I can go back and get my time domain samples by performing this operation. This is what we call discrete Fourier transform. And this is what we call inverse discrete Fourier transform. These two are essentially the counterparts of these two, right? These are, we can evaluate these using computers, right? Because there's nothing here that computers cannot do. They can multiply and divide. There's a finite sum here. And as a matter of fact, this can be computed very efficiently. But, and these two equations essentially approximate these two. To what level do they approximate? Well, there are some things that I point out here. First, this is all sampled. It is sampled in both time and frequency domain. So instead of the actual signal, you're getting the samples of that signal. Instead of the actual spectrum, you're going to get the samples of the spectrum, right? So that's one thing that is approximation. And the second thing that is approximation comes from the fact that we are only processing a finite duration of the signal, right? If you have, for example, voice, theoretically it goes forever, but you're taking just a section of it. As a result of that, you're always going to be dealing with approximate spectrum of the signal because of the aliasing problem, right? Because once you truncate the signal, its spectrum becomes infinite, and these periodic extensions will overlap one another.
Is there a scalar in front of the xn summation? Maybe a scalar needs to be down on number 2.
This is 1 over n0 here, right?
Yeah.
Well, that's one of the way how it's written. I have to check how your book wrote it. Yeah. This is what I forgot. 1 over n0. All right, so let's first prove that these formulas hold. So proof. So let x hat of t be sample version of the signal. Of signal x of t. Okay? We know that x hat of t x hat of t over period t0 can be written as x hat of t, let me put here t0, although it's not in the notes, but for you guys to know. This is sum when n goes from 0 to n0 minus 1, x of t times delta of t minus n ts. I have n0 samples over duration of t0, because remember, n0 is equal to t0 divided by ts. So that's the sample version of the signal that is over this period t0 that I use for processing. So let's look at what is the Fourier transform of this guy. X hat t0 of t is going to be Fourier transform of sum when n goes from 0 to n minus 1. Oh, sorry, this should be x of nts, right? The sample of the signal. So this is Fourier transform of n x of ts, delta t minus nts. And then when I bring this Fourier transform inside, this becomes sum when n goes from 0 to n0 minus 1, x of nts. What's the Fourier transform of this delta? It's just a delay, right? The Fourier transform of the delta is e to 1 e to the minus j and omega ts, right? So that's the Fourier transform of this truncated version of the signal. Problem with this is still not discrete as a function of omega. It still continues in omega. So consider when omega is much smaller than omega s over 2. If the aliasing is negligible, then x of omega is approximately ts times x hat of omega, which is ts times sum when n goes from 0 to n0 minus 1, x of nts e to the minus j n omega ts, for omega smaller than omega s over 2. So here's what we are saying. This is now the Fourier transform of this truncated sample signal. And as such, it gives us some information about x of omega. We know the following thing: because of the truncation, there is some sort of overlap in the frequency domain. The sampling itself introduced periodic extension, but the truncation of the signal actually made this periodically extended signal convolve with the sync, right? And that blurs some of its frequency domain characteristics. So there may be some aliasing, but if there is not much aliasing, we can say over one period, this this Fourier transform of the sample signal is essentially the same as the signal itself, the Fourier transform of the signal itself. Also, now looking at the frequency domain sampling from frequency domain sampling, we have that XR, which was X of R omega 0, was equal to TS. Now, instead here I can say N goes 0 to N0 minus 1, X of NTS times e to the minus j N R omega 0 times TS. Right? So I'm saying now, if I'm sampling in frequency domain, going every omega 0 increments, then instead of evaluating this at omega, I can evaluate this at R omega 0. So these are the samples of the signal in a frequency domain. So now, if you look at what I have here, omega 0 Ts is equal to 2 pi, omega 0 is F0 times Ts. This is 2 pi, F0 is 1 over T0 times Ts. The ratio of Ts over T0 is what? 1 over N0. So this becomes 2 pi over N0. If I plug this in this equation here, then I get that XR is equal to Ts, sum, when N goes from 0 to N0 minus 1, X of N Ts e to the minus j N R, 2 pi N R over N0. And now if I realize that this Ts times X of N Ts I define to be Xn, right? So I have the relationship that says XR is equal to sum, N goes from 0 to N0 minus 1, Xn e to the minus j, 2 pi Nr over N0, which is the statement of my discrete Fourier transform. So what did I demonstrate here? I demonstrated here that I can obtain the samples of the signal spectrum directly by processing the samples of the signal in a time domain. These X of N are the samples of the signal in the time domain. I can obtain the values of the samples of the spectrum of the signal by performing this operation here. Now, what is really interesting about this formula is if you look at here, there is no mentioning of T0, no mentioning of the Ts. By looking at this, you have N0 numbers in a time domain that you're translating in N0 numbers in a frequency domain. You have, by looking at this formula alone, you have no idea what is the sampling rate, what's the resolution in frequency domain, any of these things. You're translating N0 numbers into another set of N0 numbers. Now, what did they represent and how do they relate to the actual frequencies in the time domain of the signal? You have to actually supply additional information, and this is you have to know who T0 and Ts are to be able to interpret this problem, right? Otherwise, it's just N0 numbers into another N0 numbers. Now, there is a usually it's written like this, but you have to be careful. One thing that is not C in this equation, we don't write approximate, I don't know for what reason, but there's one big step here that we made, one big assumption that we made here. And that big assumption is actually in this step here. We're saying the aliasing is negligible. What that translates into is this T0 needs to be large enough to capture the frequency to kind of, so it needs to be large enough. If this T0 is large enough, then we're saying that we have enough samples in time domain to be able to capture all the frequencies of the signal in a spectral domain. That's, I would say, most common misuse or misinterpretation of the Fourier transform. You have to have enough of a signal in time domain for these estimates to be reliable. In other words, for this to hold. And this only holds in approximately. So, strictly speaking, this is an approximate relationship, right? Because you always have aliasing. Why do you have aliasing? Because you're processing a finite portion of the signal in a time domain. So that's a proof of the direct Fourier transform. Let's look at the inverse one, and then we'll look some examples of how this is used.
So even though we sampling at a high effort than the Nyquist, we're still going to have aliasing too?
Yeah, the nature of it is different, right? We talked, it's a very good question. Let me try to point it out. What does aliasing mean? Aliasing means that there is an overlap between those periodic extensions in the frequency domain. There are two reasons why aliasing occurs. One is, let's assume, for the sake of just explanation, to make things simple, let's assume that my signal is of the finite band, right? I pre-filter it so its bandwidth is B. So how do I get alias? One way of getting aliasing is I'm not sampling at a rate that's greater than Nyquist rate. So that is, trivial one to understand. Sampling in the time domain extends the signal in the frequency domain. If I sample below Nyquist rate, then these two extensions start overlapping. That's crystal clear. What is problematic with sampling, and we always come to this, and these are those details, right, that are always the gotcha details, right, that we always somehow forget, but they're actually the most important things here. If you look at the sampled signal, this is the sample signal, and it goes from minus infinity to plus infinity, x of nts, delta of t minus nts. Even if we forget for a moment that this delta cannot be generated, what this assumes is that you have entire signal, right? And that's you're never going to have entire signal. So, our signal is always going to be truncated. Now, what we actually have is something like this, xt0 of t, which is x of t times pi of t over t0, right? You're going to be working with a signal that is the sample signal, but only within a given window, time domain window, that has a duration of t0. Now, if you look at, we know the spectrum of this one. It's a periodic extension, right, of the original spectrum. But this is multiplication in the time domain with a pulse, which means the signal in the frequency domain, or the spectrum of this one, is obtained as a convolution between the original spectrum and sinc function. So let me draw a couple of pictures here in the frequency domain. Remember where we started. We said our signal starts as being this. It starts as being band limited. So this is our signal. It dies at B. Right, so this is x of f. Right? That's our band limited signal. Now, what does the spectrum of the sample signal look like? Well, we know that it's 0, this is fs, 2fs, and so on. Right? 2fs, And then if we sample it properly, here's my signal. Here is its periodic extension. Ugly one, too. Right, so that's my x hat of f. Right, periodically extended. I'm here sampling, there is no alias, right? Why is there no? Because my fs is much larger. Fs is much larger or larger than 2 times b, right? Because this is b, this is fs minus b, and they don't overlap. So that's the Fourier transform of this signal. The problem is n goes from minus infinity to plus infinity. So now I'm multiplying in a time domain by a pulse, which means I take this and I convolve that with sync. Now, how does the sync look like? You remember sync, right? It's like this. You know, that signal, and you're convolving, right? So you're sliding it, shifting, multiplying, and all that. As a result of that, what will happen is this signal will get blurred, right? Because sync, remember, has an infinite spectrum, right? So this signal will start being blurred. And even though you sampled at a frequency that's twice the Nyquist, larger than twice the Nyquist, and you didn't start with any alias, because you are processing the finite chunk of the signal, you end up having alias. And there's nothing you can do about it, except of making this T0 ever larger to reduce this, right? But it's always going to be there, because you're not processing the entire signal ever, right? So always keep that in mind, because the way this aliasing becomes larger, if you start shortening the window through which you're looking your signal, this is what starts happening, right? And even though you're sampling at the proper rate, the fact that your window is small is increasing this alias, and you're going to actually have a false impression about what the spectrum of the signal looks like. Go ahead.
Hey, back on the proof, we did the Fourier transform of the product there. Shouldn't that be the convolution in the frequency domain?
No, because the thing here is, where is the t here? There's no t here. This is NTS. These are constants.
That's why they go to x omega.
Yeah, there's no. This is just a number. This is a sample. So Fourier transform of this comes outside,
Okay.
and then Fourier transform only operates on this delta. So this is just this is Fourier transform of this. This is the only time domain function.
So once we sample our x and t, we don't really take a Fourier transform.
Well, these are, once you sample it, these become numbers. So they're not function of time. Fourier transform operates on a function of time. The only function of time is this delta. Right?
But n is changing with somewhat related to time, isn't it?
Yeah, but it's this. Remember how this signal looks like. This signal is this, right? You're having x. This is x of t, and there is this guy. Multiplication of these two, right?
Right.
So, and you end up with a signal as a product that looks somewhat like this. Right? These are your deltas that, this is signal that is x hat of t, which is sum over n x of nts delta of t minus nts. So if you take the Fourier transform, you end up with this whole bunch of Fourier transforms of delta
Oh,
functions.
okay, so the Fourier transform was just the delta part,
Yeah, this is the only function of time.
and that was a constant, so it comes
Yeah,
out.
the rest is a constant, comes out, right? So you end up here. The biggest thing that so far I'm kind of dwelling a lot, because it's a very important, is the finality of this sum, right? The Fourier transform originally, when we developed the spectrum of this and this periodic extension, we let this n go from minus infinity to plus infinity. We don't have that freedom. We have to integrate overflow. We have to do it in a finite time. As a result of that, you have this blurring of the spectrum in frequency domain. Okay. So, I don't even remember what was the original question, but it was a good one. Yeah, it was a good one. All right, so let's now go back. Okay, so this is, oh, okay. So in the reverse direction, consider this sum when r goes from 0 to n0 minus 1, xr e to the j m omega 0 times r. Essentially consider this sum. We need to demonstrate that this is equal to xm, okay? Lowercase x times m. So this is equal sum when r goes from 0 to n0 minus 1. And instead of this xr, I can write what I proved a little bit earlier, that this is equal n equals 0 to n0 minus 1, xn e to the j n omega 0 r. And then I have, minus here. And then I have e to the j m omega 0 r. Now, just like in any proof of this kind, what we do is we switch the orders of the summations and see what happened. So let's say I first sum when n goes from 0 to n0 minus 1. And this xn does not depend on does not depend on r, so it can go outside of this sum. So it becomes xn. And then I have sum when r goes from 0 to n0 minus 1. E to the, let me see if I use positive or negative. So j omega 0 m minus n m minus n times r. And now we know how to sum this. This is a simple geometric series. So this is sum when n goes from 0 to n0 minus 1, xn. Down upstairs I have, this is, this is e to the j omega 0, m minus n, 2, 0, 2, 1, 2, 3, plus all of that. So it becomes 1 minus e to the j omega 0, m minus n. Now, this goes to n0 minus 1, so what should I put here? n0 minus 1 plus 1, right? So it's just n0. And downstairs I have 1 minus e to the minus j omega 0 n minus n times 1, right? So that's how we sum this. Now consider now what did I, okay, so that's that part. So let's take a look at just this term here. I'm going to call that f of n minus, or m minus n. And this is 1 minus e to the j omega 0 with is 2 pi over n0, n minus n times n0. And downstairs I have 1 minus e to the j, 2 pi over n0, m minus n. And this is equal to, let's look at the two cases. What happens when n is different than n. When m is different than n, then you have here this n0 and n0 cancels. M is different than n, so this is some sort of integer, right? E to the j 2 pi times integer is 1. 1 minus 1 is 0. So the top is equal to 0. Let's see, why is bottom not equal to 0? M and n, they are both smaller than n0, right? You can see that here, right? N goes from n0 to minus 1, and this m here is smaller than n0. So their difference is always smaller than n0. So this is some fraction of n0 times 2 pi. So this is all not equal to 0. That's all I care about, right? So this never amounts to full 2 pi, right? Because this is m minus n is always smaller than n0. So this is something different than 0, but the top is equal to 0. So that when m is different than n, this whole thing is 0. When m is equal to n, what happens then? Then this is e to the j 0, and then this is also 0, right? So we have 0 over 0. Now, you can show that in limit, this is actually equal to n0. Now, how do we show that? Let me see, do I even show that? No. But I can say something like this. F of m minus n is equal, let me do this. Let me pull e to the j pi m minus n as a common, minus j pi as a common. Or, let me just have it this way. So then it becomes e to the j minus j pi m minus n minus e to the j pi m minus n. And then downstairs, I'm going to pull e to the j pi m minus n over n0 as a common. So this becomes e to the minus j pi m minus n over n0 minus e to the pi over, yeah, okay, pi m minus n over n0 j. What did I do? I took the half of whatever I have here and pull it outside, right? Why did I do that? To have signs, right? So this now becomes, here, let me just see, this is this minus this, right? So this becomes e to the j pi m minus n and minus 1, I say 1 minus 1 over n0, right? So it's n0 over n0 minus 1. Is it? No, it's n0 minus 1, right? Over n0. But that's not that important because it's going to go to 0 anyway. But here I have sine of pi m minus n divided by sine of pi m minus n over n0. And then take this whole expression when m becomes closer to n. So then you can see this as divide here by pi, divide here by pi, and so when you take this limit, you know, let me just put it over here. So this f of m minus n is going to be equal to this e to the j n minus n times n0 minus 1 over n0. And then I have sine of pi n minus n. And I'm going to just say pi n minus n divided by sine of pi n minus n over n0 divided by pi n minus n over n0, and then I have to have times n0 here. Right. See what I did? I divided everything by pi n minus n, and then here I divide by n0 and multiply by n0. Right? And then when I let m go to n, what is this? This becomes what? Becomes 1. This whole thing becomes 1, and then this n0 climbs upstairs, so this becomes n0. I just, sorry, I skipped this step in notes, but I just wanted to kind of fill it in. So this is the expression that we're dealing with, and we have two cases, when n is equal to 0, and m is equal to n, different than n, and m is equal to n. When m is different than n, this is clear 0, because this becomes 0, and this is different than 0. When m is equal to n, then through some work, we show that this is equal to n0. So now, we look at this thing here, and this simplifies tremendously, because whenever m is different than n, whenever n is different than m, this whole thing is equal to 0. So out of this entire summation, only one term survives. Which term? xn, right? So this becomes n0 times m. And then times xm, sorry. So from here, you get that xm is equal to 1 over n0 times this sum. Sum when r goes from 0 to n0 minus 1, xr e to the j m omega 0. Okay? So we got our formula in reverse. We show that we get the samples of our signal in the frequency domain by taking the discrete Fourier transform of the numbers that I sampled in the time domain, and the way back is this formula here.
Excuse me, Professor.
Uh-huh.
I have a question here. Actually, what is the main difference between regular Fourier transform and the discrete Fourier transform instead of this discrete stuff over here?
Well, what is the main difference? Let's just write them out and then see what is the main difference. These are the different formulas that we use, and let's just look at them. So here's our continuous Fourier transform. It says that x of omega is equal to integral when t goes from minus infinity to plus infinity, x of t e to the minus j omega t dt, and it gives us x of t as 1 over 2 pi integral when omega goes from minus infinity to plus infinity, x of omega e to the j omega t dt. This is our continuous transform. What it says here, we understand what it gives us. It gives us the spectrum of the signal and helps us go back and forth between time domain and frequency domain. But there are several things that limit practical use of this. First thing is these t goes from minus infinity to plus infinity. The concept of infinity in the real world is difficult concept. I'm not saying we don't understand what it is. We understand what it is. But it's difficult to deal with numerically, right? We cannot calculate easily with infinities. So what this formula allows me to do is calculate the Fourier transform of some signals. But they either need to be given to me analytically, like I know the formula that allows me to evaluate that signal for any t, or I'm stuck, right? In every real signal, if I want to calculate its Fourier transform, I have to chop it. I have to say, okay, forget about this signal goes forever. Let me just look at this portion of the signal. So this has a beautiful theoretical use and helps tremendously in explaining what we are trying to do in a lot of situations. But in terms of calculating the actual spectrum of the signal, it has a limited use, because we cannot ever integrate from minus infinity to plus infinity. We always have to truncate. Furthermore, this assumes that we know signal, every point of the signal, right? And that's not feasible either, because in majority of contemporary signal processing, we don't process the signals themselves. We process the sampled version of the signals. So there's a practical issue here. Okay, how do I make this alive in any practical application? Let's say I turn on my spectrum analyzer, how do I produce what I see on that screen?
So you need samples, right?
So I need to let the signal go through. I'm always going to sample it. And then the question is, how do I get the spectrum of that signal through this sample? And this is where DFT comes into play. DFT says, okay, you cannot really get the x of omega. Forget about getting every single point in your spectrum. I can give you discrete samples of the spectrum, right? I can get spectrum at some resolution in the frequency domain, right? And so in other words, I can get x of r omega 0. I get these samples of the spectrum in a frequency domain by performing this operation. N goes from 0 to n0 minus 1 of x n, which are the samples of the signal in the time domain. And then I have to do e to the minus j n times r. And, let me just do 2 pi n times r divided by n0. This n0 is going to be t0 over ts. It is, I'm going to look at the t0 duration of the signal. I'm going to sample it at ts. This will give me n0 points in a time domain. I'm going to perform this summation, and I'm going to get n0 points in the frequency domain. What these n0 points are going to represent are evaluation of this function at some discrete frequencies, right? Sampling of this signal in a frequency domain. Let's say I want to do some filtering. Then I take the signal, take a portion of it, then I bring it back in a frequency domain, get its frequency response.
Oh, you did bring that into frequency domain. I'm sorry, from the time into the frequency domain.
Into frequency domain. Then I filter the signal in the frequency domain, and I want to get it back in the time domain. So then I get my xn is going to be 1 over n sum when r goes from 0 to n0 minus 1 xr e to the plus j 2 pi nr over n0. So this helps me travel from the samples of the spectrum back to the time domain samples. So this is the practical use of this. This is what we actually do.
Not that CFD, right?
We cannot really do this except on paper.
Because there's no, in the word, minus infinity to the infinity.
Yeah, infinity, continuous, they're all kind of difficult concepts for us numerically. Now, continuous signal is also a very difficult concept for us when you think in terms of computers, right?
Right.
You cannot, if you say the signal is continuous, that means there's infinitely many points between 0 and 1. And I don't ever have a computer that has infinitely many, memory spaces, right? So I always have to sample. And this gives me a practical way how I deal with it. And what's beautiful about this, if you understand it, it's entirely under your control. You are the one selecting T0. You are the one selecting TS. You need to understand what are the implications of selections, but ultimately, you decide what those numbers are, and then this way you control how approximately this relationship here is. Because remember, this relationship is approximation because of the truncation of the signal in time domain. You have aliasing in the frequency domain.
Let me clarify again for this. Please correct me if I'm
Yeah,
wrong.
go ahead.
In the time domain, we have periodic and discrete, continuous and discrete signals. So that's why we need to have like discrete Fourier transform and continuous Fourier transform.
We most of the time, I mean, there are exceptions, of course, but in a settings that I'm talking about, most of the time we use discrete Fourier transform to process continuous signals. Signals come usually continuous. Your speech comes continuous. You put a spectrum analyzer, whatever you feed into the spectrum analyzer is usually continuous signal.
So we still need the continuous signals, it means.
But you have no way of doing this with a computer. So you say, okay, I have a continuous signal. What is my next step? Let me sample it. Let me quantize it. Let me do DFT, and then present that on the screen of the spectrum analyzer. And what happens is you feed a continuous signal, you get spectrum, right? And now you look at that spectrum, and you say, well, I know this is approximation of the actual spectrum of the signal. How good this approximation is. And that's where it comes when they say, okay, what is your span? What is the number of points? What is your pre-selection filter? What is that? What is that? And nobody knows how to set those things, right? Because you kind of twiddle with them and you say, okay, well, this seems okay. Well, what I'm trying to teach you here is how do you set those things? What are the trade-offs? How big this T0 needs to be? How large this T0 needs to be before you can claim that you have captured enough of a signal? How many points do you need? What happens if you select less points, right? So those trade-offs are what are very important. Go ahead.
But even when we do set everything correctly, it's only an estimation of what the
It's
signal
only
really
estimation of the signal, right? Only estimation, and usually it's a good one. Don't get me wrong. I mean, we a lot of times, these spectrum analyzers, they are good enough. You can always say, give me, 4,000 point FFT, right? And that usually gets the job done, or whatever you select, right? But so the spectrum analyzer is not a good example because it's this big of a box that sits on a bench that has pretty much a very good computer behind doing all the process. Where this becomes really issue if you start building some hardware that needs to do all sorts of things, and a part of it is doing spectrum estimation. Let's say you're doing some antenna design or doing whatever is the design that you do.
Filter design.
And you have no budget to do 4,000 samples FFT, or even 2,000 samples. So they say, this is what you have, and then you have to be able to say, okay, within this FFT, this is what my collection period needs to be. This is how many zeros can I pad. This is what happens if I'm padding. This is what happens if I'm not. I ran out of time, I realized, so I might take 15 minutes of the next lecture to wrap this up a little bit. But understanding of all of this is actually what you have to have when you design this kind of applications. And it's a little bit, I wouldn't say it's complicated, but it's not easy because it's multidimensional, and it's not easy for us to think in several dimensions. So I'll go over this again next time in a particular example. And then we'll do the review for that.
Yeah, I'm just curious with the TO and TS.
We're actually going to go to some examples and estimate what those are.
Yeah, because I think whenever you say that TO and TS is like you determine that by yourself and you take the sampling, it means you have different answer. Each one of the people has different answers.
But they're going to be close.